All right. So, now that we have spatial dependence in data, the distribution of Z will look slightly different, and we have seen that it will be different in the variance covariance matrix representation. So, now my sequence Z, which is the sequence of data points which are n data points that I have, I am going to now define it with a a location vector S. So, instead of sort of working with the sequence Z1 to Zn, I am now sort of bringing in these location indices S1, S2 till Sn, just to sort of notationally represent the data being a spatial data set, right. So, mathematical notation is just helping me give this extra rich dimension to my sequence, right. I can say Z1 or ZS1, it will not really matter, but S1 is location, it is a deterministic location, and Z is the value realized, which is a random draw from a distribution, right. So, it is a rich English interpretation of this mathematical device ZSI. This is going to be distributed again as a multivariate normal with mean mu. So, we have the same mean as the spatially independent case, but the variance covariance matrix now is given as sigma with a functional dependence on theta. Obviously, sigma is a n by n matrix. Now, this sigma theta provides me a measure of covariance of values at location ZSI and location Sj, right. So, it provides me a general covariance structure between the data, and this structure is driven by their locational differences Si and Sj. If I were to think about the matrix formulation, well, it is a n by n matrix. So, it is really a collection of all covariance Zi Zj is just an element where I and j we know go from 1 to n, right. So, we are basically looking at different combinations of I and j in this covariance element, right. So, when S I and S j, they are representing the same location, that is I is exactly equal to j, I have the diagonal elements. So, I have variance of Z1, variance of Z2, all the way till variance of Zn, right. The off diagonal elements are interesting. Now, I have covariance Z1 and Z2, covariance Z2 and Z3, sorry Z1 and Z3, all the way till covariance Z1 and Zn, right. Similarly, the off diagonal values will be non-zero and will be driven by spatial dependence in data, right. And this spatial dependence is coming from the fact that this covariance will depend on this parameter theta through the parametric variogram model representation such that 2 gamma h is equal to 2 gamma h theta, right. And we know that theta is itself in a parametric space capital theta. Now, this 2 gamma h and 2 gamma h theta will provide me a representation for the covariance structure through the fact that 2 gamma h theta will be equal to 2 C 0 minus 2 C h, right. This is a relationship, a theoretical relationship that we have studied earlier, right. So, that means that the fact that I have a parametric variogram model is the fact that I can then formulate the covariance structure in the sigma theta matrix, and if I am able to then estimate theta, I can get to the variogram estimate as well, because so long as I have theta hat ml, I have my variogram 2 gamma hat, which depends on the theta hat ml, right. So, what will really change in my analysis? What really will change is that I will now have, we will now have the following log likelihood function, right. Because my variance covariance matrix has changed from sigma squared I n to this sigma theta representation, it will provide me a different log likelihood function. So, I have ln L which depends on mu and theta. Theta can itself be a parameter, right. Oh, sorry, it can itself be a vector of multiple parameters, right. And this is going to be minus n by 2 log of 2 pi minus 1 by 2 log of sigma theta. So, the determinant of this matrix minus half z s minus mu, right, transpose times sigma theta inverse. So, I am taking an inverse of this n by n matrix, and I have z s minus mu. So, this is a little bit complicated. Well, I have a scalar entity on the left hand side. So, on the left hand side I have a scalar entity. The first entity is scalar, the second entity is scalar, I am working with a determinant value, but the last entity is more complicated. It seems it is composed of vectors and matrices. So, let us look at it more carefully. So, this z I know is a n by 1 vector, mu itself is a n by 1 vector. So, this whole entity being transposed, which is n by 1 minus n by 1, is going to be n by 1. Transpose of n by 1 is going to be 1 by n. Sigma theta is n by n, right. Its inverse of an n by n matrix is also n by n. So, I am going to have n by n, the middle part of this sandwich, and the last part is going to be n by 1 minus n by 1, the whole thing will be n by 1. Okay. Now, when we start to multiply these matrices, we can look at the first two just to simplify our lives. The first two are 1 by n multiplied by n by n. So, first thing to realize is they are conformable. We can multiply them because the number of columns in Zs minus mu is the same as the number of rows in sigma theta inverse, right. So, that is how we figure out whether or not the matrices are conformable, that is their product really defined. Here it is indeed defined, and this product will turn out to be a 1 by n, that is going to be a combination of this one here and this n here. So, once I have this 1 by n matrix, I can go ahead and multiply it with this n by 1 matrix. Again, these are conformable because the number of columns in the left hand side matrix is the same as the number of rows in the right hand side matrix, but the size of this matrix is going to be interestingly 1 by 1, which is nothing but a scalar. So, I really have a scalar entity on the right hand side, even though it might look a little bit more complicated than what we have seen till now, right. So, the fact is that I am trying to maximize my objective, again objective is to maximize, because I am working with maximum likelihood. So, I am going to maximize log ln L mu theta. Let us just write it down quickly, so that we have a consistent notes for you. Okay. So, we have a scalar entity on the right hand side. We want to maximize this log likelihood by choosing mu and theta. Okay. So, our choice variables are mu and theta, and theta itself is composed of components like nugget and B, C0 and B for linear model, for linear variogram model, right. In case of spherical model, we had the nugget, the sill and the range. So, the number of choice variables will depend on which variogram model do you want to work with as an analyst, right. Whether you want to go with the linear or the spherical is your choice. So, I am going to say this is the analyst's choice. Okay. Whichever way you go, you can write down the first order conditions, solve them, and you will have, I am going to say this exercise will yield theta hat ml, right. That is, in case of a linear variogram model, we will have C0 hat ml and we will have B hat ml, right. Once you have that, you will also have a data driven variogram 2 gamma hat h comma theta hat ml, which is nothing but C0 hat ml, which is now a value data driven understanding of spatial dependence, which is exactly ml, b hat ml and h. So, this is the data driven representation of what is the nugget in my given sample, and b hat is the rate of decline in spatial dependence as we move away from any given location by a lag vector h, right. So, we have a data driven entity of b hat and C0 hat ml. You shouldn't be you should not feel terrified by these things. One of the very the reason is that although these algorithms, when we work with them, they look mathematically intensive and sort of tedious, most of these are going to be canned. So, towards the end of this course, we will study we will do hands on tutorials on R, which will provide us software syntax which will directly spit out the theta hat ml and the variogram estimator given the data set you have. But it is very important to know when you work on these software, typically what happens is you write a code, you run a syntax, and a black box works which basically is maximizing all of these things, and it is eventually giving you the final answer. We will always use the final answer, but we should know what is happening in that black box, because when you work with real world data sets, when you work with complex problems, when you do research, you can't really rely on what the software is giving you. If you don't understand what is happening behind the scenes, in all likelihood you are going to get stuck at some point, or your explanation of the physical world will come out to be nonsensical sometimes, and so on and so forth, right. If you understand the machinery, well, great, use the software, right, use the convenience of computation to actually calculate these things, but that does not discount the value of learning the process as it goes on mathematically. Okay. Now, there is a very important note that I want to give you before I end this maximum likelihood estimation, is that ML estimates theta hat ML are biased, right. Why? They are biased because they do not account for these, do not account for the degrees of freedom. Okay. These do not account for the degrees of freedom. And what does it mean for us to say that it do not account for degrees of freedom? For this we will refer to the IID case, where we had sigma hat squared ML equals summation I equals 1 to n z I minus z bar the whole square divided by n. Now, earlier in this course when I wrote sigma hat squared, I said it is rather n minus 1, and this n minus 1 accounts for a loss of degrees of 1 degree of freedom, because of the fact that in this definition I have already used z bar. That means, although I am using z1 to zn, by using also the knowledge of z bar, I could have used any one of one less of this sequence of z1 to zn. Let us say I did not know zn, I only knew z1, z2 all the way till zn minus 1, and I also know z bar, I can back out zn. That means, in the definition of sigma hat squared ml, I am using the net variation of n minus 1 values given the knowledge of z bar, and hence in the denominator I should have had a n minus 1 and not n. But when you solve those first order conditions in the IID case, we can look at them now. When we solve these two first order conditions, the sigma hat squared ml that comes out does not account for the loss of degree of freedom, right. So, this loss of degree of freedom loss remains unaccounted. This is very, very important. It's really a fundamental knowledge that ML estimates are fundamentally biased for the variance covariance estimators, and the bias becomes larger and larger the smaller the data set that you are working with. Okay, so the next algorithm for achieving a fit of the variogram is called as the least squares algorithm or the least squares estimator for a variogram model. Okay. Now, as we move forward, remember we started with experimental variograms, right. What were experimental variograms? Well, it is just 2 gamma h of j. So, the hj means h1, h2, h3, h4, so different lag values in a given direction E, right. So, hj is nothing but the lag vectors in a given direction E, right. That is, I have h1, h2, h3 and keep going till hn, or let us say h, let us not use n because n is the sample size, let us say hk. Okay. Okay. So, I have for the experimental variogram I have manually gone in, chosen k different lag values, formed a vector of these lag values and evaluated the variogram cloud for each of the hj lag values in a given direction, let us say east west direction, and then did this for all different lag values. So, k is the number of lags. Okay. Now, the variogram model on the other hand will be given as 2 gamma h j e, but with a parameter vector theta. Now, theta we know is C0 and B for a linear model, right, and theta could be C0, Cs and As for a spherical model, right, and so on, right. So, we have these different starting points. So, as an analyst we should perhaps do it more than one variogram model to see which one is providing me a more sensible interpretation. Okay. So, the least squares algorithm is as follows. We are trying to, first of all, we take a difference between 2 gamma h j, that is the true value, which is the observed value, the data, minus the model, mathematical model form, which is either it could be linear or spherical or whatever. I take this difference for every h. Okay. Now, obviously, if I know the value of h, the value 2 gamma h j theta will simply be a function of theta, right. So, I can take this and take a square of it. So, it is a squared difference. So, the farther away you are from the given observed data, I am going to penalize you by a square. This squared difference is minimized because I want a least squares, right. So, I am squaring and then I want a least squares, and that gives me a least squares algorithm. For known h values, the only variable in this entire formulation is theta. So, my choice variable when I am minimizing is going to be theta, right. So, this exercise will give me, right. So, this will provide theta hat least squares, that is going to be, let us say, C O hat least squares and B hat least squares. Now, remember C O hat least squares or B hat least squares are alternative estimates for the same model parameters nugget effect and the rate of decline in spatial dependence through a different algorithm called the least squares algorithm. Earlier, we evaluated C O hat or C 0 hat ML and B hat ML. We just have alternative estimates of the same here. Okay. Now, I must specify that this is for a linear variogram. Okay. Now, the difference, so the least squares algorithm has a few properties. So, we are just going to call them notes. The first point is that the least squares algorithm provides a direct estimation of of a variogram based on spatial dependence, right. Now, this is different. So, I can say as opposed to the indirect ML estimation procedure. Why was ML indirect? Because ML was first using the variance covariance structure. So, it goes indirectly towards the variogram estimation, right. So, indirect because it is through the variance covariance matrix sigma theta, right. But that does not make maximum likelihood less legitimate in any way. It is also going to be slightly biased, but still maximum likelihood is very tractable, and it is also allows for very different it's much more general than least squares, something that you will realize as you work practically with data. The second point with least squares is that you can incorporate multiple directions can be incorporated by adding the respective squared differences. Okay. So, if you add, if you go back to this formulation, I mean, you basically are saying that you just need to sort of add all the different squareds, right. So, here I have sort of done a short typo. I should add the least, the squares, right. So, I have squared the differences, but I should have added them from j equals 1 to k. So, if I add these more squared differences for let us say direction E tilde, I could simply just add them here and minimize the whole sum together for 2 different directions or 3 different directions and so on and so forth. So, incorporating different directions is not so problematic or not so complicated with the direct estimation process of least squares as opposed to what it would have been for the indirect maximum likelihood procedure. Okay. The last topic that I want to touch upon in today's lecture is called as the generalized least squares algorithm. So, this sort of is sort of motivated by the fact that we have a sequence, just like we have a sequence of data Z1 to Zn, right, and for this sequence of data we can write the mean and we can write the variance. Similar to that, we have a sequence of these variogram values. So, we have this 2 gamma at h1, 2 gamma at h2 and till 2 gamma till h some k value, right. So, we really have a vector of let us say k by 1 values of 2 gamma, just like, remember we had this vector for z as well, this was a n by 1 vector, z1, z2, zn, this. For this vector of data, right, we could write a mean value z bar and we could also write a variance of z bar, right. We can simply calculate these things given the data set that we have. Similar to that, there is going to be a variance of this 2 gamma value. Okay. I mean this 2 gamma is nothing but a vector. So, I can just define it as slightly differently here. So, I should be able to now figure out a variance covariance structure of this value. Now, k by 1, if I have a vector which is k by 1 size, the variance covariance vector will be a k by k. So, I am really looking at variance of 2 gamma h1, variance of 2 gamma h2, so variance of 2 gamma hk, but then also covariance between the experimental plot at location 1 and location 2. So, not only the data will exhibit spatial dependence, but in some way even the variogram will exhibit that, because you will have covariance with lag h1 and covariance with lag h2 and so on and so forth. So, if you have such a structure where there is a variance covariance matrix such that you do not have the off diagonal elements being 0 or all the diagonal elements being equal to each other, then the least squares estimates are inconsistent. And what you really need is a GLS algorithm, right, which looks like the following. So, just like in case of OLS we are going to minimize with choice variable theta, but now my my formulation of what I am minimizing is going to be different. So, I am going to define this V as the variance covariance matrix, or I could say it is omega, let us say. Okay, I have omega and omega inversed 2 gamma minus 2 gamma theta. So, I have a slightly more complicated function to minimize. What you will realize is if you look at the size of this, you will see that it is also a scalar 1 by 1. Let us do that, right. 2 gamma by itself is a k by 1, 2 gamma theta is going to be k by 1, the whole thing transpose is going to be 1 by k, sigma inverse is k by k and this is just k by 1. The first two together is 1 by k and the that then multiplied to the last matrix is going to give me 1 by 1. So, I am really minimizing a scalar value with respect to theta. I will write my first order conditions, but this will yield theta hat GLS and not just LS. It is a generalized least squared estimate, right. It is more robust and it is a consistent estimator. So you know, if you are interested in more information about this, you can go back and read it from Cressy's book. As far as getting to these values, you know, you have all of this, you are going to have all of this scanned in software, and we will do this in, you know, you can study this when you are you know, looking at the software, you know, hands-on tutorial. But the point of the matter is that if you had a more complicated variance structure of the variogram, the experimental variogram, which is going to be likely, right. If the data themselves are, you know, spatially dependent in the second moment, then the variogram is nothing but the representation of a second moment for an intrinsically stationary data. So, that means that the second moment of this you know, variogram representation is likely to be more complicated than what the least squares would you know, assume. That is, the diagonal elements are the same and off diagonal elements are 0. That is the least square assumption, which may not be realistic. What may be realistic is what we have seen on you know, the slide in front of you. You must go over today's lecture one more time. They are a little bit more involved, and you must read Cressy's book. It's this material is in chapter 2, and you must read it from the book as well. Okay. So, thank you very much for your attention. We will going forward, we will study, you know, we will look at variogram estimation in situations which are a little bit more interesting, such that, you know, the spatial domain may be non-stationary, or it might exhibit long-term trends which does not let these spatial domains to be stationary. They require a little bit more than what if we were to simply assume stationary domains, and, you know, in real world we may not always come across stationary domains. So, we will go ahead and study that in the next lecture, and through that we will then introduce spatial prediction and study what is called as spatial kriging. Okay. So, thank you very much for your attention, and see you in the next lecture.